So, welcome, boys and girls, ladies and germs. A new mini session in our Euro Stoxx 50 application, and here with vector analysis. So, we're still in the session on getting a first look at the data. We downloaded from Wiki the tickers you got from Yahoo Finance, the daily return data, got rid of some obvious data mistake, and in SAP closing prices. Adjusted close. And now we also identified are returns Gaussian, yes or no. So surprisingly, often single stocks are Gaussian. And now the question is, do these 42 stocks that we have follow a low dimensional vector structure? That is useful for modeling because keep in mind, if all of the 40 stocks would be perfectly correlated, then you would have 41 time series with redundant information. All right, that's the idea of vector analysis. You want to figure out, is there a low dimensional representation of the variation in the original data? All right, and that's what we do here. So we start in that video to talk about how many principal components are necessary to explain, let's say, 95% of the variance in the underlying 43 blue chips, or 42. We will see how many there are. And we will also have a look at how important is the first PC, the second PC, so on and so forth. Okay, so let me just do the coding. Well, we kind of start with the vector analysis. It's still rather simple, just getting to know the data here a little bit. Okay, so I just continue with the sheet. First look at data, which means we already loaded in a couple of packages, pandas, numpy, matplotlib. And there's a package we need today because we don't develop the code ourselves in the first look at the data session, right? But we just take the Python packages, which are really beautiful. So what we do now is we take from sklearn decomposition import PCA. If you don't know about PCA, you want to know about the analytics of PCA, look at our other videos that we have. They explain kind of eigenvalue decomposition, what's principal component, and how to do the rotation, so on and so forth. All right. Okay. Now let's just remind us, what is RD again? RD.hat, right? Assuming you haven't seen the previous videos. So RD hat. All right, so we have 43 firms, but one is the 1/n portfolio. So we have just 42 firms. And they start in 2000 and go all the way back to just check. Okay, great. 9th of November 2020. Okay, great. So what we now want to do is we want to apply a PCA to that RD, but we don't want to incorporate the 1/n portfolio. Okay. So we just define an object PCA of our daily return data, and that shall be PCA, which we just loaded in the function .fit. And what shall you fit? Please fit it's a bit small, is it? Yeah, I think I like that better. What shall you do? I want you to my goodness. I want you to fit the entire panel here. rd.ilog, yeah, so go for the full time series. But don't take all the objects. Only go up, exclude the 1/n portfolio, which is rd.shape1. As the counting starts in 0, we subtract 1. Okay. Now it's going to exclude the 1/n portfolio. Otherwise, it is doing a PCA here. And now we want to visualize how much of the variation in the panel is explained by each of the PCs. Okay. So the way we do that, we make a nice plot. We loaded in matplotlib library. And therefore, we also load in the NumPy library, and NumPy has this function called cumSum. So we want the sum of eigenvalues divided by all the eigenvalues, and the upper sum just goes for the number of PCs. That was really technical. Basically, we just want to see cumulatively how much variance to explain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 PCs. So we have PCA RD, that's our object. There's a function in that, it's called explain variance ratio. Okay, and we want to display the plot in terms of pluses. It's easier to read. So plt.xlabel, what's on the X label? It's the number of PCs, and plt.ylabel, that would be the cumSum of variance explained. Okay. So what you see here is that we have 42 stocks. So at most we can have 42 PCs. If you work with 42 PCs, you explain 100%. So there's no obvious redundancy. That's what we see, right? If you want to explain really 100% of variations in all of these stocks, you need all of the stocks. But what you also see is if you just work with one PC, that is kind of a bit hard to read here. Therefore, we make it more explicit. That's the cumulative sum. We now also want to get how much variance explains each PC. All right. So we just do print, and then instead of summing it up, we just get the individual ones. And let's look at that. Okay. So you see that the first principal component explains 45% of variance of the underlying return panel. Is that a lot or not? I would say it's not bad because we have 42 firms from across the Euro area, across different industries. The common theme is these are the blue chips of the Euro area. And we see that 45% of the variance of a single stock out of that panel can be explained by just one principal component. Yeah, so that differently, we can extract one factor, and that one factor will explain roughly half of the variance of all other stocks. All right, now what is that factor, PC? Well, that's a linear combination of the existing stocks. A linear combination of the existing stocks. It's a linear PCA, what we do. Now, what about the second factor? The second factor explains only 5%. The third factor, 3%, 3%, and then it goes down to 0, 0, 0, 0 at the end, right? So kind of, I said you need all the factors, but if we get rid of the double zeros, yeah, kind of need everything to the left in order to explain basically 100% or 99.9% of variance. Now, what we also know is if you have a 1 over n portfolio out of 42 stocks, you have something like 2.3% weight put on every stock, or 2.6, something like that, let's say 2.3. Which means if all the stocks were perfectly orthogonal to each other, then you would think that every PC adds 2.3%. Therefore, when I see something here like 5%, that kind of in my thinking from just tells me that kind of two of these stocks which have such a common information, and that looks really very much stock specific. So I'm already inclined to say that a one-factor model would explain 45% of the variance. In our notation or language I used previously, it just kind of tells us that there's a hypothesis, which I'm now stating, roughly 50% of A Stoxx variance is diversifiable, while the other 50 is systematic. What the heck is that again? Well, systematic risk means it's risk you cannot diversify. And since one factor drives 45% of variation across all stocks, it kind of tells me that that systematic factor, it looks like that is my PC1. I will have another video coming up. Not sure when, just look at my cheat sheet, but it doesn't say. So there will be one video coming up where I really check whether this PC1 has any similarity to the market portfolio. Right? Okay, great. But at least we have 45%. If you really want to, maybe that's good homework for you, test whether PC1 makes a good vector in terms of representing the other 42 stocks in terms of a single factor model where the single factor is PC1. How do you do that? Just run regressions of stock returns on that PC factor, look at the residuals, and check that the residuals across 42 firms are uncorrelated. If they are, then they're really idiosyncratic, firm specific. And then, from statistical point of view, you found a well-specified single factor model. All right, that's all for the moment.